be logging in as we get going. Sorry about that. I had the microphone kind of close to that. Well, we all know. Anyway, I am pleased to open this meeting. I'm Terry Denny. I'm the president. We have a couple of guests today that are visiting us. So I'd like to welcome you all, and we'll take a moment to introduce our visitors to the meeting. So we'll start back here. Say your name and how you found out about us.
Hi, I'm Mac Johnson. So I found out about this. So I work here in the museum, and just by pure chance, I ran into Terry during my lunch break. The rest is history.
Well, welcome, Mac. I'm so glad you made it. Do we have some other folks that are visitors? Well, welcome, everyone. I'm very excited today. Our guest speaker is one of our grant recipients. I thought that Don was going to join us virtually, but I don't see him on here yet. But I know he has a lot going on at home. So, but Don Rideout worked out the schedule to have our speaker today, and I'm not quite sure if I'm pronouncing her name correctly, but Helena Kwarteng. I'm going to let her introduce herself anyway, but we're excited to have her today to speak to us virtually, and hopefully our technology will work. Victor, the picture's gone out.
That's weird.
Give us just a second to try to retrieve the picture back here.
Where did the picture go?
I don't know. We have been a little frustrated trying to get the Wi-Fi to work in this room and the projector to work in this room.
It was when you wrote in front.
Yeah,
This is not. This is only.
I know, but that shouldn't have done anything. Let's just try this again and just see if you can hook it back up to the computer. Thanks for your patience at home while we figure this out. Yes, unfortunately, hybrid meetings are difficult to work out.
Of course, it's been on for an hour.
Oh, wait, something's coming, maybe. And maybe, Helena, if you can go ahead and share your screen, that way we can see when it comes back up. Okay.
Should I stop sharing? Oh,
just leave it like that right at the moment, and that way when we get our picture back up, we'll be able to see it. I can see it on my computer, it's just not projecting. If you want to go ahead at least and introduce yourself and tell us a little bit about yourself while we're working on the picture, that would be great.
okay. Okay, so I'm Helena, and thank you so much for the opportunity given me to present to you on my MS thesis project. So I'm a grad student at the University of North Carolina at Wilmington with the Department of Earth and Ocean Sciences. So as it has already been said earlier on, I was part of the recipients for the award from this organization, and I'm very grateful for that. My MS advisor is Miss Patty Mason. And basically what I'm doing for my MS thesis project is using foramniferal isotopes to kind of reconstruct past climate conditions from the late Cretaceous to the early Paleocene times. Can I go ahead with the presentation?
Yes, we have, we had the picture and now it went out again.
Go ahead.
We have some light. It's too dark and I can't see to fix the computer.
So as we may all know, anthropogenic climate change is currently one of today's most pressing issues. And what I mean by anthropogenic here is, it's being related to human activities. So for instance, this has been proved by scientists with the pace at which carbon dioxide is being released into the atmosphere, and also being able to kind of trace the fingerprints with this carbon dioxide back into the times when humans began to burn fossil fuels. Even though this issue of climate change has been around for the past few decades, it's not surprising that we are still at a point where there hasn't been any, major solution to fully combat this problem. We ended up crossing the 400 ppm atmospheric CO2 concentration threshold in 2016. And that is what is being indicated with this green lemon green line here. So this graph is a study that was done by Kwarteng. They started measuring the concentration of carbon dioxide in the atmosphere from 1960. And from this diagram, it can be seen that CO2 increased with time. So they made this graph in 2016, and the wiggles that you see here is just indicating seasonal changes. But then on averagely, or even with the wiggles, it's still obvious that the concentration of carbon dioxide in the atmosphere increased with time. So even though there wasn't any major physical damage at this time, it was a big deal for scientists at the time because they realized we were entering into the danger zone of climate change. And it's not surprising we are seeing some of its effects in
Can you hold,
instances.
can you hold a minute? Because we're having some more issues with the picture.
Okay.
Ask a question while we're waiting. Can you tell us what the 400 mark means? Is that a known factor in going to be future problems, or is it just an arbitrary number that was picked?
No, so it's from the time that humans have existed, there hasn't been any case where we've experienced atmospheric CO2 concentration going even beyond 300 ppm in the atmosphere. So scientists realized that if we cross this 400 ppm ppm concentration, then it's probably kind of indicates that we are entering into the danger zone of climate change. So it's a danger zone for them. I don't know if that makes sense.
Yes, it does. And does this, are they sure that this is because of the increased emissions of CO2 by us, or is it anything to do with our relationship to the sun as we get closer?
Yeah, so that is why I mentioned earlier on that they've been able to see so much evidences, and that is being able to trace the carbon dioxide back into the times when humans started burning fossil fuels. And also, we've seen volcanism and events like volcanism and asteroid impacts in the past, but then we are not able to trace the current CO2 or carbon dioxide in the atmosphere into any of these natural cycles, in addition to the sun, and also the pace at which it's occurring. If it was a natural cycle thing, it wouldn't be so fast continuously over a long period of time.
We have the picture back. So you can go ahead. Hopefully this will be the last interruption.
Yeah, I hope that made some sense.
Yes, thank you.
Okay. So we are seeing the effects of, climate change in so many instances today. I'm sorry about that. I don't know why it wasn't moving.
That was not
Here or there. I know.
Yeah, so for instance, we saw a record-breaking flood in Tennessee last 2 years, which destroyed most homes and was all over the news. Arizona has also seen its mega droughts in the past few years. The Great Barrier Reef is also seeing a massive coral bleaching, and as we can see, most of the corals in this terrain are dying. We've also seen extreme wildfire cases. And when we consider the case of wildfire in California, it has been observed that the wildfires that are occurring recently are much more hotter and larger as compared to the ones that happened a few decades ago. So this issue of climate change has been a major problem for all of us. And in an attempt to kind of help solve this problem, the Intergovernmental Panel on Climate Change was set up. And the Intergovernmental Panel on Climate Change is also what is being referred to as the IPCC. So the reason why this organization was set up was to help evaluate the science of climate change. So they create, as part of what they do, they create assessment reports on the current states of knowledge with regards to climate change. They assess the impacts as well as future risk, and also propose mitigation strategies. So the image that you can see right here, it's showing us the logo of the Intergovernmental Panel on Climate Change. As part of what they are doing to help solve this problem, especially considering the case that CO2 is still increasing at a much faster pace, they thought of the need to kind of start making projections into the future. So they use multiple scenarios, and the fancy term they use for these scenarios is the representative concentration pathway. So as you can see, the RCPs here, they are just different scenarios. So for instance, we have RCP 8.5, 6.0, 4.5, and 2.6, basically meaning different scenarios. So when we consider something like the RCP 8.5, this is a scenario where climate modelers or climate scientists are expecting that by 2100, everything will get to its peak, like everything getting to extreme conditions continuously due to technological advances, which is causing more fossil fuels to be burnt. When we consider the case of RCP 2.6, this is also representing a scenario where climate change begins to decline in 2020, and probably we get into zero emissions by 2100. The RCP 4.5 is kind of an intermediate scenario between these two. And when we consider the RCP 6.02, it kind of reflects everything getting to the peak by 2080 and then beginning to decline. So as we can see on this diagram, it can be observed that when we consider the RCP 8.5, which is the extreme scenario, we see the concentration of carbon dioxide in the atmosphere going beyond 1000 ppm, somewhere around 1002 ppm. And this is very devastating because we've seen similar conditions in the geologic record, and it led to the destruction of the ecosystem, which makes it a bit worrying. So in as much as climate scientists have been able to come up with these projections, it has been realized that there are errors in the modeling. probably due to clouds and moisture. And it's not surprising because these parameters are very complex and it's easy to kind of quantify them, thus integrating them into the models. So it creates the need of getting something that can help validate these modeling or projections. And to be able to do this, we can't think of any other thing other than looking into the geologic record and seeing if we'll come up with conditions that were similar to what we are experiencing today or what we are hoping to see in the next few years. So when we consider, based on studies that have been done, when we consider the late Cretaceous to early Paleocene, this condition is thought of to be similar to the projection that we saw in the RCP 8.5, mainly because during this time, there was a massive volcanism during the late Cretaceous, and there was also an asteroid impact at the Cretaceous-Paleogene boundary. This led to the destruction of the ecosystem, and it's not surprising that there's this notable event that occurred, which led to the extinction of the dinosaurs. So that was the time that dinosaurs went extinct. Now let's think of it this way. We've seen errors in the models. We want to validate them. We've gotten to realize that, oh, okay, so we can use records in the past to be able to validate these models. But when we talk about late Cretaceous and early Paleocene, we are talking about ages that, you know, kind of revolve around somewhere 50 to 60 million years ago. So how are we going to do this? Obviously, we can't go into the past to take these measurements physically. And we were all not there during those times. So to be able to do this, we rely on methods that we call proxies. So for instance, when we consider the proxies, we have a variety of them, and this includes the tree rings, we have foramniferal fossils, we have sediment cores, we have ice core, and we have corals. So when we consider something like the tree rings, the thickness in the rings kind of helps us have an idea about what exactly was occurring during those times. When we consider something like foramniferal fossils, because they build their shells from the ocean, and a lot of carbon dioxide in the atmosphere changes the chemistry of the ocean, we are able to tell what the environment was like when these organisms were building their shells. And the same is with corals as well. When we consider ice cores too, the water molecules obviously react with the molecules in the air. So they kind of leave imprints for us to have an idea about what was happening during those times. And when we consider the case of sediment cores too, the layering also gives us a clue to what was happening during the time that these sediments existed. So among these proxies, one of the proxies that remain very useful and has been used over time is the foramniferal fossils. And in my next slides, I'll be expanding on the late Cretaceous to early Paleocene, as well as the foramniferal fossils. So now let's look at the late Cretaceous to early Paleocene. So the late Cretaceous is the last epoch for the Mesozoic era. So this is just a geologic timescale that I created based on some data that I had. So the late Cretaceous is the last epoch for the Mesozoic era, and the Paleocene is the first epoch for the Cenozoic era. So with the age range that I will be specifically looking at between this interval, I'm looking at ages ranging from the Santonian to Danian. And this corresponds to somewhere around 86.3 million years ago to about 61.6 million years ago. So as we have already seen in the previous slide, this time, the late Cretaceous to early Paleocene was being characterized by extreme events, and that's the volcanism and the asteroid impact. So when these events occurred, they ended up releasing massive greenhouse gases into the atmosphere, which eventually led to the global warming or causing the Earth to warm. And numerous studies that have been performed in this area have seen that the concentration of carbon dioxide during this time reached over 1,000 ppm. which makes so much perfect sense to kind of validate some of the models that have similar extreme conditions. Now moving on to the fossil Foramnifera. Foramnifera simply refers to microfossils or single-celled organisms with shells. So they first appeared in the Cambrian. And we have two different types. We have the planktonic forms and we have the benthic forms. So the planktonic forms refers to the ones that dwell at the surface of the ocean, while the benthic forms refers to the ones that dwell at the bottom of the ocean. So the images that you see here give some examples of these forms of the forams that we have. So this first image shows some examples of benthic foramnifera fossils from the late Cretaceous period. And the one on the right here shows examples of planktonic forms also from the late Cretaceous. So personally, when I am behind the microscope trying to differentiate between these two broad types, I always kind of see the planktonic forms to be in a shape of popcorn. And I also see the benthic forms to kind of be snail-like, even though we have some few exceptions to all of these. Another major component of the foram that is very necessary to look at is the test. And the test is basically the shells of the foram. So they can either be calcitic or aragonetic. So in the case of the shells, for instance, understanding why it's necessary, I'll just give a brief example of how it makes sense to use them. So for instance, when we consider evaporation occurring at the surface of the ocean, most light carbons, that's carbon-12, is being evaporated into the atmosphere, and they get precipitated in the polar regions and then get trapped in ice. So in the case where climate change is occurring and the earth is warm and these ices are melting, it obviously means that the carbon-12 that was being trapped in the ice will be released into the atmosphere. So if there was a foram occurring at that time, forming its shell at that time, then it means that obviously the foramnifera shell will be enriched in the light carbon isotope, that is the carbon-12. Same with carbon-13 and same with other stable isotopes. So this makes it very useful. It can also be useful because we realize that different species existed in different environments. So for instance, some in cold regions and some too in a little bit warm environments. So in the case of one species called Grembelytra cretacea, we even realized that it is an opportunist. So it's always around, or it always occurred in extremely harsh conditions. So getting to know about all this, I then had to kind of decide on what exactly I wanted to do for my thesis project. So I first decided to kind of review articles that have used foramnifera fossils to reconstruct paleoclimate. So from the review that I did, I realized that most of the studies focused on the Cenozoic, and it's just a few that focused on the Mesozoic. So that is what I have indicated in the map here. With the ages that were outside my range, I indicated them with a cross, and the ones in my range, I indicated them with a check. So you realize that there are so many crosses here as compared to the checks, which obviously tells us about the fact that, oh, okay, then most studies have been done in the Cenozoic. And with the reason being that some of the Cenozoic conditions are also similar to the projections being made by the IPCC. But I think it will be very necessary to also look at somewhere around the Mesozoic if we are having conditions that were similar to the RCP 8.5 projection. So in the case of North Carolina, I realized that there has not been any study done on the Mesozoic, particularly from the Santonian to Banyan, using foramnifera fossils for climate reconstruction. So I therefore decided to focus on this boundary then for my project, or this area then for my project. So obviously, if I'm considering focusing on this area for my project, then it means I'll have to get samples from the area. Fortunately for me, 5 cores were drilled somewhere between 2003 to 2006 for subsurface geological investigation. So these cores include the Dixon core, the Smith Elementary core, the Elizabethtown core, the Hope Plantation core, and the Prairie Beach core. So the Smith Elementary is my main focus area, and that is what is being indicated in red. The other cores are also represented in purple, with Dixon being represented in pink. The reason why I represented Dixon with pink is because if I have much time, I'll reconstruct the paleoclimate for Dixon as well and compare the results that I see from these 2 cores. So now, what is the main goal of my study? The main goal of my study is to reconstruct the Santonian to Danian paleoclimatic conditions of the Smith Elementary core. And to be able to achieve this, I have to meet these objectives. So first, being able to pick and identify 300 Foramniferal species from 3 of my samples. Then once I do this, I'll be able to identify the common species that appear in all of them. Once I'm able to get this, I'll just focus on picking the commonly preferred species from the remaining samples. And after getting this, I'll take the test of the species into the isotopic lab to run the oxygen and carbon isotopic analysis. Once I'm done with the analysis, I'll be able to interpret them based on carbon and oxygen. So for instance, interpreting ocean circulation or temperature and salinity based on delta 18 oxygen, and also interpreting biological production based on delta 13 carbon. So after getting to know this, it was necessary for me to have my samples. And for the Smith Elementary core, I'm using 40 samples in all. 34 of the samples were already available and were just handed over to me by my advisor. But then I went to the North Carolina core repository in Raleigh, that is the North Carolina Geological Survey core repository, to collect 6 additional samples to help extend into the Santonian. And during the sampling, I sampled the cores at about between 9 to 10 feet interval. So after taking the samples, I then brought them into the lab and decided to disaggregate them to be able to, get the individual constituents. So I did this by soaking my samples in Calgon solution for about 24 hours. And after soaking them, I then decided to wash them under a running distilled water through a 63 micrometer sieve. After I was done with the washing and got rid of all the muddy, particles, I decided to wet sieve them using a filter paper. And that is what you can see in the image right here. After wet sieving, the samples were then ready to dry, and I dried them in an oven at about 45 degrees Celsius. Once I was done with the drying and gathered the sediments that I've gotten, I then brought them to the lab to be able to pick them and identify them under the microscope. To be able to do this, the tools that I used include the brushes, the picking tray, the slide, and the Chagocalent gem. So basically, the slide is where I pick the forams and stick them on. Then this one is kind of like a glue. So it helps the foram stick on the slide. Then the picking brushes, obviously, to pick and help turning the forams for identification. So the microscope is what I use to kind of identify them, and that is what you can see in the image right here. So after identification, I try to categorize the different species in separate boxes to kind of make them easy for me to keep track. So that is also what you can see here. And the Foramniferal fossils are very tiny, like very, very tiny. That is why you cannot see them very clear here. Now, after I'm done with this, I'll double check the species that I've identified with a scanning electron microscope. And right after that, they will be ready for the isotopic analysis. So I'll be performing the isotopic analysis at the UNCW's Isotope Ratio Mass Spectrometry Core Facility, which is at the Center of Marine Sciences. So all the samples that I'll be using will be brought to this lab and will be analyzed for their oxygen and carbon compositions. The instrument that I'll use to run the analysis include the thermogas bench and also the stable isotope mass spectrometer. Once I've been able to retrieve or get the individual constituents, that is the carbon and the oxygen, I'll then try and report them in the standard per mole notation by using this formula that you can see right here. And the image above this formula, it's an image that I took in the mass spectrometer lab at CMS. And this also right here is some of the tools that I'll be using to help with the analysis. After getting the results, these are the interpretations that I'll be making. So for instance, considering delta oxygen 18, if I see more negative trend, it means the temperature during that time was warm, and obviously salinity decreased. If I see more positive, that also indicates cold temperature and also increased salinity. Now, in the case of carbon delta 13, when I see more negative, it indicates decreased biological productivity. And when I see more positive trend, that also indicates increased biological productivity. After I'm done with all these studies and all these analysis, I'm expecting my results to be similar to what is already in literature. So I hypothesize that the results from my studies will be similar to past studies that have used the same technique to reconstruct past climate conditions from the Santonian to the Danian. And for my project timeline, I am expecting to kind of get to the point where I'll begin with my isotopic analysis in fall 2023, and obviously writing my thesis and submitting them for draft revisions. I'm hoping that by spring 2024, I'll be done writing my thesis and defend and obviously publish at the latter part of the semester or afterwards. So thank you so much again for giving me the opportunity to present my work to you. And I'm sorry I couldn't make it in person. I'm hoping that by the time I'll be done with my studies and will have the opportunity to present my final results or findings to you, I'll be able to join you in person. Thank you so much, and I'll be glad to answer any questions that anybody may have. These are my references. Thank you. Yeah.
Linda, I think we see that you have a question.
No, I was just clapping.
Oh, okay, we couldn't tell.
Sorry, it wasn't a raised hand, it was a clap. It's okay.
Okay, we have a question here.
And then we'll
Okay.
get the other one.
Helena, if your results don't end up being the way your hypothesis goes, where do you go from there?
If my results were,
If your results end up not being similar to what you're predicting it to be, then where do you go? Do you have to do more research?
yeah, so if my results are not similar, obviously I'll publish what I got from the studies that I made. But then in the case where, in the case where my results are not similar to what is already in literature, then another thing that I can also do is going ahead with my PhD project and probably considering another terrain using the same technique and looking at the same period to see if it will still be, it will still not be similar to what is already in literature. But then from my opinion, I think everything I see from my results is what I have to publish, because everything out there, even though there's been so many studies done, we cannot justify the fact that everything is accurate until we keep doing numerous experiments to kind of prove or disprove what is there. I don't know if I answered this well.
Thank you.
Yeah, thank you.
We have another question.
Mhm.
Hi, Helen. I noticed we did not see much of that Keeling curve because we didn't have a picture, but you said in the beginning that 400 parts per million had been reached, that's of CO2 had been reached in 2016. And then you showed that it was 406.58 ppm in January, I think was that 2017? This is in the beginning of your talk. But I looked at that curve yesterday and the number was 423.
Yeah, so that is because if I'm getting your question right, me showing somewhere 400 and you saying 420 as of yesterday, right?
Yeah.
Yeah, so that is because CO2 is still being released into the atmosphere because we are still burning fossil fuels. So we are still seeing an increase of carbon dioxide in the atmosphere amidst all this problem. And that is the main reason why the climate scientists realize that, okay, then it will be good to even start making projections into the future, since we've still not gotten to the point where the emission can even be stopped.
Right, and so I just was actually pretty shocked at how much more had gone into the atmosphere in such a short period of time. So looking at, I don't know if you showed that curve looking over.
Yeah, so I can show that.
It's vertical. Because Linda had asked a question earlier about could this be due to being closer to the sun or something like that?
Mm-hmm.
Clear that the human effect is huge.
Yeah, yeah.
Okay, well, and I don't think you actually showed that particular curve that I'm talking about, which is the Keeling curve in over a great amount of time, and it shows the end of the curve being vertical. It's still pretty impressive. Thank you.
Yeah, thank you too. Thank you so much too.
We have another question.
Yeah, hey, it's James Bennett. Dude, that was a great talk. Quick question. You mentioned early on that the shells of these forams can be either calcite or aragonite, much like we see in the Paleoclimactic fossils. Do you get the aragonite ones as well as the calcite ones in your sample from those cores, or do the aragonite ones all dissolve away? Thanks.
Yeah, so I focus on the calcitic ones to perform the isotopic analysis based on what I've seen in literature.
Here's another question.
I was intrigued with the Foramniferal. How close to age when you find these can you get, like within 10,000 years when you see one, as far as if you're trying to age a specimen?
Yeah, so the earliest forms appeared in the Cambrian times. And for the period I am looking at, that is from the Santonian Sudanian, so which is about 86.3 million years ago. And if I'm not getting it wrong, then the Cambrian is, I think, around 540 million years ago. Yeah, so that was the first time that they appeared. So we can always use them for past climate reconstructions into the Cambrian. Any time beyond the Cambrian, that is the Precambrian, before Cambrian, we cannot use forams for reconstruction. We can only use them for the times that they begin to exist or began to exist, sorry.
I believe his question was more in how close can you age a specimen? How close can you come to exactly how old it is? I think that's what he was asking, not the general ages of them. But if
Right,
you have a
Helena?
specific specimen,
Yeah.
Oh,
Yeah, I think he's asking, are there index forams like there are index fossils so that you can know what time frame you're looking at?
yeah.
Okay.
So the forams is not just used for paleoclimate reconstructions. They also helps us in identifying the age that we are looking at. So with Foramniferal fossils, they don't give the absolute ages, they give relative ages. And a characteristic of them that helps in determining the ages is they being index fossils. So once we are able to get the relative ages from forams, we confirm the ages with other methods that gives absolute ages. And that is when we are able to kind of decide on the fact that, oh, okay, so this is the age of the forams that we are looking at, and then go ahead to reconstruct the past, the environment.
thank you. Are there any other?
I hope that answered the question.
We do have another question.
Okay.
Hi. Just trying to get my thoughts together. So I think you may have touched on this a little bit, but I just would like a little further clarity. What would you say are advantages of using forams or foraminiferans, I think is the proper term, in studying paleoclimate as opposed to corals?
Okay, so I'm not very sure about the answer to that, but then different organisms exist during different times. And for the period that I am looking at, I am not very sure if corals existed at that time. But then from literature, it has been observed that Foramniferal continue to remain, one of the most useful organisms to kind of reconstruct past environmental conditions. For corals, I'm not very sure if they existed during this time, but then forams have been tested several times and they've been proved to give the best indications. But that is something that I'll have to kind of look further into.
Okay, cool. I will say I do know for a fact that corals were around that time. I actually did my own independent research back in college on biodiversity through time. So,
okay, then I think that is something that I'll have to further look into and find the answer to this.
We have another question.
It's not really another question, it's just a follow-up to Mac's question. I think your answer is that forams are very specific to certain environments. Is that not correct? I mean, corals are affected by environment too, but isn't it that forams are very good indicators of salinity or temperature or something else, and they're very specific to those quantitative pieces of data.
Okay, that makes sense. Thank you.
I'll also jump in and say that I think forams are like ubiquitous. So if she's going to use core samples to be checking for the right time frame and time period and past, she's going to find a foram a whole lot faster than she's going to find a coral or anything else. So just about anywhere you look, you're going to find a foram because they're so tiny. Whereas finding a larger macrofossil is going to be a lot more challenging, especially if you're looking at time frames for things that are subsurface. She can't go and collect them on the surface. She's having to use core samples to find the age that she's looking for. So that's probably why forams were the better thing to pick in this category, because she could actually get them.
Yeah. So to add that, basically they are characteristic as an index fossil. So evolving quickly, they being found everywhere. Yeah, and also being easy to identify. Yeah. I see another hand.
Sorry, that was me. I forgot to put it down.
Okay.
How did our grant help you, Helena?
It really helped me. It really helped me. I was able to use part of the money to go to Riley to be able to sample the course, and I was also able to use it for some of my laboratory stuff. So I would say it really helped me. Yeah. Thank you so much for that grant. Yeah.
Do we have any further questions here? It looks like we've answered all the questions